really excited to Thanks, Anthony. We're really excited to welcome you all to our first GeoDAWG seminar of the year. It's 2023, but we're still stuck in that time where 2022 is getting written everywhere. So we'll correct that for next time. But we're very excited for Chih-Ting to give her presentation today. Just a couple quick announcements that we normally do at the beginning of these. You can check the upcoming seminar for some of the ones coming up this year at our website. It's the link at the top of the page there for the seminar. If you haven't already, please sign up for our mailing list. We will be sending out notifications and stuff as well as workshops that I'll kind of go over on the next slide. And then if you have any speaker suggestions, please feel free to fill that in there. We're really looking forward to highlighting some of the really great work done in this field. And like always, we'll be recording these talks and then uploading them to YouTube. So if you miss it, please check out our channel and you'll be able to rewatch this presentation there. And we just sent this out to our mailing list before. We just wanted to highlight a few upcoming events that are happening this summer. The first is the IUGG conference, which abstracts are due February 14th. So get those in soon. There's a really great session on data assimilation and statistical learning that is really well connected to what we're doing here at GeoDAWG. And then that's in Berlin, in Germany. And then we will be following that up with the GeoDAWG workshop right after. And registration deadline is July 3rd, and the URL link is here at the bottom of this slide, and we'll also make sure to post that in the Slack for you so you can be able to update that in the Zoom chat, sorry. So you can be able to update that soon. So please, if you're interested, please apply for both of these events. We really look forward to seeing you there. So I'll pass it on to Anthony, who will introduce our speaker for today.
All right, thanks, Adam. Welcome back, everyone. Just a friendly reminder is please keep yourself muted unless actively speaking. And then Chih-Ting is happy to take questions during or have a longer discussion section at the end. So it's up to you when you ask your question, but if you do, either please raise your hand or enter it in the chat first, and then we can call it out at the right time. So with that, we welcome today Chih-Ting Hsu. She is currently a project scientist at the NCAR High Altitude Observatory with a background in ionospheric radio occultation data assimilation and weather prediction. And so today she'll be talking to us about some of her more recent work. So Chih-Ting, thanks for joining us today, and feel free to take it away.
Okay, yep, hold on. So can you see my slide right now?
Yes, looks good.
Okay, cool. Okay, hello everyone. This is Chih-Ting Hsu from NCAR HAO, and so today I'm very happy to have this opportunity to share with you, join the seminar and share with you our research result about the thermospheric data assimilation. And so I would like to thank Tomoko to invite me here. And also I would like to thank my co-author, Nick Patatella and Jeff Anderson. Okay, so first of all, I would like to, in the first slide, I would like to give a quick overview of the goal of this study. So we all know that if we have a set of thermospheric data, and we can use the data assimilation to assimilate this thermospheric data into a numerical model of thermosphere to improve the weather and the monitoring, thermospheric weather monitoring and prediction. And then if this numerical data is not just thermospheric data, but a couple model of thermospheric, if this model is not just a thermospheric model, but a couple model of thermosphere and ionosphere, then the updated thermospheric state will also change the ionospheric state and affect the weather monitoring and forecasting in the ionospheric part. So here, just show a quick cartoon, simple cartoon of the to give you an idea of the general idea of this study. So the green line here is a true state, and this is the true state for a neutral state, a thermospheric state, and this is the true state for an ionospheric state. And the dark blue line showing here is the simulation result from the numerical model. And the green star here is an observation. So at this model time step, we can assimilate this atmospheric data into the model to bring this numerical model state closer to the truth. And then meanwhile, even we don't touch the ionospheric part, the ionospheric state will still be gradually become closer to the truth because we already changed the thermospheric state, and this will change the model physics and further affect the ionospheric part. So in this study, our targeted ionospheric thermospheric state is, okay, so the targeted thermospheric state is the horizontal wind in the thermosphere. And the ionospheric state we focus on in this study is the electron density distribution in the ionosphere, but more particularly, we will focus on the EIA. And in the data, so in this study, in one sentence, we will use the coupled data assimilation of the thermosphere and ionosphere and assimilate the wind data into it in order to improve the EIA monitoring. And when we do the data assimilation, there are several important information. The first one is the observation information and the observation error covariance. And also we need the information about the background error covariance from our numerical model. So one way to estimate the background error covariance is use the ensemble method. That means instead of run one model run, we can run the model many times with different drivers, different forcing and different initial condition. And then you can see that this dashed line is the model state from different ensemble members. So we have 3 ensemble members here. And then we can estimate the background error covariance from this model ensemble. And then we can do the data assimilation. And theoretically, after data assimilation, the ensemble mean will still become closer to this truth. So basically, in this study, the model we are going to use, of course, need to be a couple model of thermosphere and ionosphere. And we are going to use WakaMax in this study. And then next, the data assimilation method that we use is so-called the Ensemble Adjustment Common Filter, EACAF, provided by DART. This is also a kind of ensemble-based data assimilation method. And for the observation, we are going to assimilate neutral wind data. So we are going to assimilate the neutral wind data that sample from the ICON MIGHTI. So in this presentation, I will quickly do a quick introduction for these 3 components. And after that, because this part of this study focus on a more technical part, so I need to do a quick introduction of the ensemble adjustment common filter. And then I will show you how can we tune the ensemble adjustment common filter with a so-called delocalization function. And then we will use the observing system simulation experiment to test the performance of data assimilation with different settings. Finally, I will have a conclusion for this research. So first of all is our data. The data that we use is the horizontal wind data measured by ICON MIGHTI. I think most people here already know what is the ICON mission. So here I just do a quick introduction of what data we really assimilated in this study. So the MIGHTI instrument on board ICON can measure the neutral zonal wind and temperature profile. Neutral horizontal wind and temperature profile. And here, in this study, we will only focus on the wind data. And here is the trajectory of the ICON and the associated zonal and meridional wind profile. So you can see that it can provide us the wind data from 90 to 300 kilometer altitude. And we will assimilate both zonal and meridional wind within this range into our system. And next, let's talk about the data assimilation system that we use. The data assimilation system we use here is the WACA Max Dart. So DART is so-called the Data Assimilation Research Testbed. Is a software that developed by NCAR. And it's a software that can provide an ensemble-based data assimilation environment. We are going to use the Ensemble Adjustment Common Filter, EACF, provided by DART to do the data assimilation. And on the other hand, the WACA Max is the general circulation model for the Earth's troposphere, stratosphere, mesosphere, thermosphere, and ionosphere. So it can simulate the coupling process between the thermosphere and ionosphere. And WACA Max Dart has the performance of WACA Max Dart has been tested, and many papers has been published in the past. But in this study, we will only focus on the thermospheric wind data assimilation. So next, I would like to do a quick introduction of the EACF. Before I jump into EACF, I would like to start with from the very beginning, talk about what is a common filter, and then we will talk about EACF. I think most people here already know what is common filter, but in case somebody is not very clear about it, so I just want to do a quick introduction. So assume that we have an observation called YO, and we know the error of observation called R, and then we have a model state before data assimilation called XB, and we know the background error covariance PB. Then based on this blue and red part, we can get the data assimilation result, which is this black part. And the real equation look, the update equation in the common filter look like this. So it's very simple. Basically, it's the XA, which is the model state variable after update is equal to the XB model state variable before update plus a term that related to the difference between the observation and the simulation result. And the K is so-called the common gain, which is related to the background error covariance and the observation error covariance. Okay. But the background error covariance, as I mentioned in the very beginning, is estimated from model ensemble. Then we come to the ensemble common filter. And so the update equation become these two lines here. So this is the first line is the update equation for the ensemble mean, and the second line is the update equation for each ensemble member. The lowercase n here is the index for each ensemble member, and the uppercase n is the ensemble size. So you can see that basically those terms that related to background error covariance are estimated in like this is from the model ensemble like this. So that means if we only have a limited number of model ensemble, there will have a sampling error. And how to generate those model ensemble and what's the appropriate size of model ensemble is always a question. Okay, and then in 2001, Jeff Anderson proposed ensemble adjustment common filter based on the original ensemble common filter and traditional common filter. So the relation between the X, Y become this. I'm not going to detail how we derive, how we get this formula, but basically you can compare this equation with the original traditional common update equation. So it's clear that this one is the increment of ensemble model state variable, and this is the increment of observed state variable. And the B here is so-called the sample regression coefficient, which is also estimated from our model ensemble. And it's related to the correlation between observed state variable and model state variable. And alpha is the localization function. I will detail the alpha in the next few slides. So because this B is sample from is related to the correlation between observed state variable and model state variable, and it's sample from the model ensemble. So we might have some sampling error in this term. Although it's hard to show how the B looks like in EAKF, but here I just plot out the correlation as an example to give you some idea. So this, if we have an observation location at here, this yellow dot, then we can compute the correlation coefficient between the zonal wind at this point and each model grid. Then we can get a map like this. The x-axis is longitude and y-axis is pressure level or altitude. So you can see that the correlation coefficient is very noisy in this figure. And this four figure, we just change the observation location. So you can see that in all these four figures, the pattern is very noisy, and they will have a very large impact even if the observation is very far from the model grid. And we are not sure whether this structure is due to the sampling error or it's what the correlation really like in the neutral real atmosphere. So what we can do is to use a localization function to localize the impact around the observation location. So this is the localization function alpha. And the most widely used localization function is so-called the Gasparian-Kohn function. It's a parameterized localization function. So here is an example of how it would look like in a 2D domain. So the Gasparian-Kohn function is basically a Gaussian-like function, and it will only relate it to the distance between observation location and model grid, shown in the red as the red point here, and also is parameterized by a length scale called L. So this length scale can define how wide this white part would be. So you can see that this structure is comparing with this one. This one is unsymmetric in vertical direction, but this one is basically symmetric in vertical direction. So if we apply this alpha to our correlation coefficient, the result will look like this. So just here, this one, and apply this to it, and then you can get this figure. So you can see that now the impact will be localized around the observation location, and but the result is, and all the noise are filtered out, but it also shows an symmetric structure in the vertical direction and horizontal direction, and we don't know whether this is the best solution to do the localization. So one main point in this study is to find another way to do the localization instead of use Gasparian-Kohn function. So one way to do so is replace the empirical localization function, replace the parameterized localization function with an empirical localization function we call ELF. This method is also developed by Lily Lei and Jeff Anderson in 2014. So if we only have one observation and one model state variable, then the relation between X and Y shown in the EAKF can be written as this one. And all variables here are scalar. So now we can compute the error, and if we know the truth, we can compute the error after data assimilation with the truth. So here, this is the model state variable before data assimilation, and this is the increment. So basically, this is the result after data assimilation, and XT here is the truth. So we can also write it as a function. This part can also be written as a function of alpha. And then we can try to find the alpha that can minimize the error. then we can get how large the alpha should looks like. But please note that all variable in these three equations are scalar. So if we have more than one observation and then our model is a three-dimensional model, that means we have more than one model state variables, then the arrow should be a root mean square arrow look like this. And we still can use this equation and try to find the alpha that can minimize the E. But the alpha here will still be a scalar. So if we want this alpha can change with the observation location or the distance between observation location and model grid, then we have to first, before we start the computing, we have to group the pair of model state variable and observations by the observation location or the distance. Sorry, I forgot to mention that the lowercase k is the index of the pair of model state variable and observation, and the uppercase k is the total number of pair. Okay, and after we group those pairs by observation location and distance, we can compute the alpha for each group, and then we can get a group alpha that change with distance or observation location. Then another question is, how do we know what is the truth? So one way to get this alpha is we can compute this alpha from the OC result, because in the OC, the truth is already known. So we can use OC result to compute the alpha. And what we actually do is, first of all, we run the OC. And second, from the OC result, we can group the observation by observation location. And in this example, I group it by the altitude range. So now the observation we group it into three subsets. And for each subset, we can compute one alpha. So now we first compute the alpha for the subset of this observation, the pair of observation within this altitude range and the model state variable at this model grid. And then we can loop through the whole model domain. And then eventually we can get an alpha for this group of observation that change with as a function of the distance between observation location and model grid. And then we can repeat the same things for the second group of observation. Then we can get another alpha for this group of observation as a function of the distance. And then I can repeat the same thing for the third group. Then eventually we will get 3 alpha, and each alpha is a function of distance. So after that, we can apply this kind of method to our MIGHTI data. First of all, we separate the zonal wind data from the meridional wind data. And after that, we group the zonal wind data by altitude range from 90 to 125, 125 to 175, 175 to 225, and then 225 to 300. And then for each altitude range, we can compute one alpha. And we can do the same thing for meridional wind, and eventually we will get 8 alpha. And this red dot is indicate the observation location. The x-axis is the horizontal direction, and the y-axis is the vertical direction. So you can see that overall, the alpha pattern is asymmetric in the vertical direction. And then it shows that you have in the horizontal direction, the longer the distance, the smaller the impact. Now we can apply this alpha to the correlation coefficient that I shown in the previously. So this is correlation coefficient that I already showed previously. And then this is the result if we applied GC function to this correlation coefficient. And this is the result that if we apply the ELF to the correlation coefficient. So you can see that in both these two results, the noise in the lower atmosphere are filtered out. But in this one, it shows an asymmetric structure. We have a larger impact to the model grid that above the observation than the model grid that below the observation. So I don't know how you think about this, but I think this correlation is more reasonable. But next, we need to prove that this can really help the performance of data assimilation. I think somebody typing something in the chat, or it's Tomoko, sorry. Okay, so to show the result with different empirical localization function, we are going to run some observing system simulation experiment. In our observing system simulation experiment, the truths are WACA-max run that different from the ensemble member. And then we can sample some synthetic data from these truths and assimilate them into the ensemble member to bring the ensemble member closer to the truth. And the benefit of using OC is that because this truth is already known, so we can do a comprehensive comparison between the data assimilation result and truth at any given time and given location and given variable. By doing so, we can have a more comprehensive vision of what's the difference between different data setting in the data assimilation. So here is some details. Okay. Here is some detail of the OC that we are going to launch in this study. First of all, the first one is in the first two OC, we will going to assimilate icon data. And in the third OC, we will not. And in the second one, we will replace Gauss-Parent function with the ELF. And please note that in all these three OC, we will assimilate lower atmospheric, we will do the lower atmospheric data assimilation. And the ensemble size is 40, so it's a pretty small ensemble size, and we will expect a huge sampling error. And so that makes sense to try to reduce the sampling error by different kind of localization function. And the data assimilation window is 6 hours. And we will only focus on low solar activity and quiet geomagnetic condition. So please note that because the data assimilation that we use in this study is 6 hours. So it's hard to do the data assimilation for like a storm time. We must need a shorter data assimilation cycle to reproduce that kind of weather. And in this data assimilation, we will do, in this experiment, we will do a 1 month data assimilation. We assimilate the data every 6 hours and run it for 30 days. So now let's move to the result. Excuse me. So for the result, we expect that first of all, we do the data assimilation for the neutral wind. So we should see some difference in the neutral wind before and after data assimilation. And after that, this change in the neutral wind will further change the electrodynamic process in the WACA-max. So, and change the plasma drift. And eventually it will change the structure of EIA. So first of all, I will show you the neutral wind structure in different OC. And then I will show you the plasma drift. And finally, we will look at the NNF2 and EIA from different OCs. So first of all, it's the neutral winds. This plot is the Riemann square arrow of zonal winds. This is the time from the first day to the very end. This is 30 days. So this is how the global Riemann square arrow change over time. And then we separate them by altitude range. So this is the Rumi square arrow below 90 kilometer altitude. This is the Rumi square arrow within the 90 kilometer to 160 kilometer altitude. And this one is from 160 to 230 to 300, and above 300 kilometer altitude. And please note that our icon data will only within these 3 panels. We still have a few data above 300 kilometer altitude, but it's almost only a few data points. So basically, within this domain and this moment, we almost have no data, no icon data, sorry. And the red line here is the Rumi square from the OC with the icon data and using the ELF. And the blue line here is the one with the icon data, but with the Gauss-Parent cone function. And the black line here is the icon data, the black line here is the one without any icon data. So first thing we can see is that in all these 4 panels, we can see a significant error reduction in the first 10 days. And after that, the error become more stable and have a periodic day-to-day variability. And then you can also see that within this 4 panel, the red line, which is the one with icon data and ELF, is always the smallest. We always have the smallest error. That means the icon data and ELF can help us to improve the zonal wind specification in the model. And next, we can see that above 300 kilometer altitude, there's the error reduction is still very significant. So that means the icon data can help reduce the wind specification even within the part that there's that without any data. But however, below the 90-degree altitude range, these 3 lines are very close to each other, means that icon data has no impact in the lower atmosphere. So overall, if we look at the average improvement over the whole data assimilation period, with the help of icon data, the wind specification can be improved by 11 to 12%. But if we apply ELF, this improvement can reach about 16 to 18%, which is, I think, is quite significant. And next, let's look at the Rumi square arrow for the meridional winds. So this is in the same format as previous slides, but for the meridional winds. And you can see that we still can see a very significant error reduction at first 10 days. And after that, the error become more stable. But comparing with the zonal wind, it's hard to tell which one has a better performance in this 3 altitude range. But we still can see that the red line shows the smallest Rumi square arrow within the 90 to 160 kilometer altitude range. And I also have to point out that you can see a quick error increase at the first date of the data assimilation. And we guess that this might be because of we also do the data assimilation for the lower atmosphere, and that might introduce some perturbation to the thermosphere. But we need more detailed study to investigate what's the reason, real reason of this error, the increase of this error at this point at first date. And generally, the meridional wind specification can be improved by 3 to 6% if we assimilate icon data, and can be improved by 7 to 10% if we apply ELF. And next, let's move to the plasma drift. So this pattern is just the plasma drift in the true state. So the x-axis is local time and y-axis is the date. And you can see that we have an upward drift in the day side and downward drift in the night side. And we also have a clear day-to-day variation in the true state. And then the next 3 panel is the difference between the OC result and the truth. So we want this difference to be as small as possible. You can see that in all these 3 panels, we have a large difference at very beginning of data assimilation, and then the difference will reduce over time and become stable, as what we can similar to what we have in the Roomy square error of the winds. And then if we compare these 3 OC results, you can see that the one with icon data and empirical localization function shows the smallest difference here. And then we can see, let's look at the Roomy square error of the plasma drift. I separated by day side and night side. So you can see that basically in the day side, the red line, which is the one with ELF and icon data, shows the smallest error in most of the time. And we can see an error reduction significantly in both day side and night side Roomy square error. And basically, generally, the icon data can help improve the plasma drift specification by 12%. And if we add ELF, the improvement can reach 18%. Okay, so next is the NNF2. So again, this is the true state of NNF2, and this 3 column are the difference between the truth and the OC result. And we can see that this is the snapshot at day 5, 10, 15, 20, 25, and 30. So I would say it's hard to tell the difference between these 3 results. From at very beginning, you can see it's almost the same, although there's still some small difference. But after day 20 here, we can see the one with ELF and icon data has significant error reduction comparing with the other 2, but still have some room to improve, like this part. And if we look at the Roomy square error of NMF2 at mid-low latitude region, you can see that I separated by UT time. And in the day side, the red line shows the smallest error at the end of data assimilation experiment. And in all these 4 panels, the red line shows the smallest error after day 20. And overall, if we use we assimilate icon data, the error reduction, the NMF2 specification can be improved by about 10%, which is not very significant. But if we use the ELF, the NMF2 specification can be improved by 8%. So I think it is quite well with the help of ELF and icon data. So generally, we can conclude that with the help of thermospheric wind data assimilation and empirical localization, we can improve the ionospheric weather monitoring. And here come to our conclusion. So first of all, we proved that icon wind data assimilation can help improve the thermospheric wind monitoring and forecasting. And then just the thermospheric wind data will further change the plasma drift and NMF2 predictability through the electrodynamic process in the Wacom Max. And this can further help us to improve the ionospheric weather prediction and monitoring. And then with the help of ELF, we can have a better data assimilation performance. And for our future work, as I mentioned previously, in this study, we only focus on 6-hour data assimilation, which is not enough for if we want to do the weather prediction for storm time. So we want to have a shorter data assimilation cycle in order to do the storm time weather prediction. And then the next thing is that in this study, we only focusing on the observing system simulation experiment. So we need to, in the future, we need to move to the observing system experiment, which means that we want to assimilate real data to test the method that we use is really work for the real upper atmospheric weather prediction. And yeah, that's all my presentation, and thanks for your attention. Yep, I can stop here and take any question.
All right, wonderful. Thanks very much, Chih-Ting.
Thank you.
Yep, sure.
So I think Fazl's question was addressed in chat, but if you still have a question about that, feel free to ask.
Hold on.
And then if not, maybe Tomoko, we can go to your first question.
Yeah, Chih-Ting, thank you very much for a very nice talk. And then you spent, thank you for putting really nice introduction to get us on board. So about ELF, did you consider ELF only in a vertical direction, right? Or
both vertical and horizontal.
Horizontal directions. Do you know the sort of, I guess, so I could see the impact of asymmetric sort of, localization function in a vertical direction, and then it looks like it's really helped that lower thermosphere.
Mm-hmm.
But do you see that sort of impact of ELF in a longitudinal or local time directions? Because that's also, in the upper atmosphere, there is a large changes over local time. Yeah, right. So I guess it's a both, I guess. But
yeah, so it depends how you, as I mentioned, it depends on how you group the observation. So in this study, I didn't group it by the local time, so you cannot see those structure. But I think if you group the observation by local time and compute the ELF for each local time, it might, the structure might change with local time, of course. Yeah, but I didn't do that, so.
Yeah, thank you for explaining. I think, just going through the chats, and then I think Wenbin one had also had a similar question, so you might want to answer that. Unless
Wenbin has a question. Yeah, is the ELF had the same for longitude and latitude? Yes, it's the same for longitude and latitude. So the y-axis here is represent the horizontal direction, but not not represent the longitude or latitude. So basically, I only compute. So this represent anyway. It represents horizontal direction, the horizontal distance. Sorry.
Yeah,
so it's not it will not change with longitude or latitude. But we can do that. But the point is that it will take more computing time to do so. Yeah.
Yeah, okay, thank you. I think I'll let other to ask question. I have some other question related to slides, but
yeah,
maybe Anthony or Adam, do you want to tell someone?
Sure, I think Lewis had the next one then. He asked, how's the lack of data over the South Atlantic anomaly affecting the outputs?
I'm not quite sure. I didn't focus on that region. Sorry about that. But I think because we only have we only use the icon data, so you only have one data profile at each single time. I think we don't have lots data amount, and that's why we want to use ELF, because they can optimize like our the impact of each data point. But I didn't focus on that region.
Okay.
Is that answer your question?
Yeah, thank you. I wonder because in some of the plots that you showed, the southern border of the Equatorial anomaly looked very thick, and I wonder if that has to do with this lack of data. But it might not be.
Right.
Maybe just something to consider.
Yeah, I will take a look. Yeah, thanks a lot for your comment.
Sure.
Yep.
Thank you.
Great. And then Fazul had the next question.
Was the line of sight value integrated mechanism will be considered in the forward operator? No, we didn't do that. We didn't consider how the MIGHTI compute the zonal and meridional winds. We just simply sample the wind data from the location they provided. Is that?
Yeah, okay.
Mhm.
Just a clarification on the earlier one, like I was asking about what's the difference between like one case GC and one case MIGHTI GC, and Nick said it's difference between is like one case MIGHTI has not been used, and so that does it mean like what are the other data were used like?
You mean the data?
Was it like lower atmosphere, SEBR, and those things, or?
Look, well, could you say that again? Sorry, I didn't hear that.
I mean, like one case MIGHTI wind was used, and in another case MIGHTI wind was not used. So what else the data were used?
Oh, okay. I think I have a list there.
Oh, sorry, I missed it probably.
Yeah, no problem. So here is all data that we use. We also use the conventional meteorological observations.
Oh, thank you. Yeah, now I remember. Yeah.
Okay. I think next question is from Art. Yeah, the Alfred Long.
So if I understood the view graph correctly, the ELFs, you showed a large, well, altitude and longitude range. And for large longitude separations, I think was it the next one or the previous?
This one?
Yes. So those, I'm wondering about those blue regions, which indicate negative values for the localization function. And I think that can be physically reasonable. I'm just wondering, did you include those negative regions for the localization function when you did the assimilation?
Yes, we include this part because I think this just shows that you have a negative correlation between these 2 points. So what we have is that the localized function is always positive. It's between 0 and 1. But for when we apply that to our correlation, sometimes it will be positive and sometimes it will be negative. Just shows the nature correlation between 2 variables.
Okay, I misunderstood. This is not the localization function on the right, but rather localization function times the correlation coefficient.
Yeah.
All right. Thanks.
And is there any other questions? Oh, okay. In your experiment, does ensemble common filter provide a greater protection against the data noise or bulges observation? Do you still need to precondition with input to the data? I'm not actually quite sure about your question. Can you
hello. Yeah,
hi.
This is Ivan. Yeah, you see, if the observed data that goes into Kalman filter prediction scheme is bad for various reasons, the instrument did not do the right thing, there was a calibration issue or something, then that mistake will continue promote itself into the further stages of the prediction. I was wondering if you if you have a protection against obviously erroneous inputs to
Yeah,
the
we
filter,
do have.
do you build that?
Yes. So in Dart, you can, there's a function that you can turn on that you can reject all data that without standard deviation from the model. So that can protect to assimilate bad data into it. And we also will filter out those data that has bad data quality.
Okay, that makes sense.
Mm-hmm.
But I was wondering if that ensemble technique that you're using when if multiple versions are working in parallel would improve your protection against the data.
No,
not
it
really.
won't.
Okay, thank you.
I have one more question about tides.
Yeah, sure.
So ICON, one of the science objectives is to get that, to want to get tides, I guess. Upper atmospheric tide has been a global scale waves, been such a, omnipresent force that drives all the dynamics. So question is that two things. That one is that so distance-based localization will probably, it's going to destroy well, will absorb this, the global scale correlations. It just has to, have you really see the impact of it, or like, have you given some thoughts to that? And then the other thing is that you want to see the impact of MIGHTI in addition to MLS and then SAVOR. But I'm just curious that have you considered doing some OCs, or have you done any OCs on the impact of MIGHTI versus SAVOR plus MLS impact on the tidal diagnostics? Or so there are two questions about tides. Have you looked at how well assimilation of those data are doing better on tides, improving tidal characteristics? And then one is, have you maybe distance-based localization will probably destroy their correlations.
So I think, sorry, go ahead.
Yeah. So that's one question.
Okay. So the quick answer is no. We didn't look at how this localization will destroy the tide. We have think about that. But actually, it's a bit hard to do the localization in the tidal space, because you need to like at least 1 day's output, right, to get the tide, and then then the question would be like, when you do the data assimilation, are you going to do which time step are you going to do the data assimilation? You cannot. So for example, I compute the tide for 1 day, and are we going to do the data assimilation at the end of this date, or what? Are we going to do the data assimilation for like 24 hours or something? That's I think is very costly, and it's a very complicated question. So we think about that, but we don't.
Yeah, you can characterize tides, using snapshot model output, but I think it's a difficult question. I was curious. Yeah, I just more for the discussion, I guess. It's a challenging. Yeah.
And and we also didn't do the comparison between different OCs, the performance of tide representative with different OCs. Yeah, but I think it's a good question. And we think about that, but it's hard to really like do the comparison.
Yeah, it's not fair, because I know it happens. Okay, good. Thank you.
Yeah, thanks. I think Fazil have a question for everyone. Tomoko, do you want to?
Shida Mint, yeah. Do you wanna organize for us? I'll help you, Fazil. Well, so this GeoDAWG is not just a Shida community. So we there's a strong presence of magnetospheric community that they have different sets of, or similar sets of, but also unique challenges. Yeah, so see that gem meet, but yeah, that's a good idea. Yeah.
Yeah, okay, thanks. Yeah. So I have a last question, like OSI MIGHTI ELF, in this case, ELF was used for all the data or only icon data?
Oh, that's a good question. Sorry, I didn't forgot to mention the ELF is only used for the icon data.
Okay, thanks.
Yeah. I think one very important point is that we don't have much data in the upper atmosphere, and that's why we want to use ELF to maximize the impact of each data point. Any other questions?
No, well, if there are no other questions, I'd like to first just thank Chih-Ting for a really, really wonderful talk. You generated a lot of really great discussion, and thank you all for showing up today to our very first GeoDAWG seminar. Please be sure to check our website for the upcoming seminars for the rest of the year. And then also, if you're interested, please check out the GeoDAWG workshop coming up in July in Germany. We'd also really love continued collaboration there as well. So thank you again, Chih-Ting, and be on the lookout for this on our YouTube channel if you'd like to watch it again. So thanks so much, everyone. We'll see you next time.
Thank you, Chih-Ting. Thank you very much.
Thank you.
Bye.
Thank you. Cheers.